Do 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 do. Do 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 do. Main objective of this lab: to become a master at adding vectors both graphically and by components. Bah, bah, bah. Tools you will be rocking today in lab: the ruler, protractor, 4 mass hangers, different slotted masses, and of course, the force table. Alright, so when we're talking about adding vectors, it's helpful to, know what a vector is, right? You gotta know what you're adding. Okay, so first we're gonna go ahead and start with a line. Now it's a special line, but it's not a happy line. It's got a length or a magnitude of some arbitrary amount, but it's not a vector, so it's not happy. It's actually a scalar. Yeah. Now we put an arrow at the end of our length, and it's like, wow, I got direction. I know where I'm going. Magnitude, direction, that is a vector. Woo! Oh yeah, good times. So, quick note on the notation we use to define a vector. You have your letter or symbol with an arrow over it. That's it. There's the notation for a vector. Okay, 2 ways to define a vector. Vector, 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 vector. So you have its magnitude and its direction, or angle theta from the x-axis, or you can define it by its scalar components. Let's talk a minute about these scalar components. So you have your vector, and sadly he's stuck. And you want to define its scalar components. So first you have to have its angle theta and its magnitude. Okay? And then when you have those two things, you can plug them into these handy dandy formulas right here. Ax equals a cosine theta, ay a sine theta, and solve for its scalar components. Let's do an actual example. Big blue. Okay, so we want to define its magnitude by measuring it with a ruler. Keep in mind the accuracy of a ruler, and then you're going to use the protractor to measure its angle. So you're going to line up the x-axis with your 0 and measure to where the vector lines up with the best angle. Here it's 35 degrees. And then you're going to plug and chug. So solve for ax first. Ax is going to equal a cosine theta, and we're going to plug in 24.5 centimeters cosine 35 degrees, off-screen calculation time. Then we get this awesome number of 20.06 centimeters. Take into account significant figures, 20.1 centimeters. Now, that's your AX component, your scalar component for the x-axis. Now, I want you to do the AY component on your own. You should be getting 14.1 centimeters. If you don't, check the mode on your calculator. Make sure it's in degrees. If not, life's not very fun. Okay, so adding vectors graphically, basically with pictures. You're going to use the head to tail method. So basically you have vector A. You want to add it to vector B and get a resultant of vector R. So vector A, the head of vector A is going to be attached to the tail of vector B, and the resultant is going to go from the tail of A to the head of B. That was a mouthful. Now say you have multiple vectors that you want to add, so A, B, C. So go ahead and, well, in the lab you'll have them defined, a magnitude and a direction or angle. So go ahead and draw it out. So you're going to start with vector A. You're going to measure out 3.5 centimeters and 90 degrees from the 0 axis, 0 degree. Now, when I'm drawing these, watch that I'm actually using the same 0 degree every time. So it's not like I'm taking my 45 and then tilting my protractor and saying that that's my new 0. No. Okay, so head to tail method, real quick, fast and easy. Tail of the second is attached to the head of the first. Resultant vector goes from the tail of the first to the head of the last. Again, a mouthful. Adding vectors by components. So you have vector A is defined by AX I hat plus AY J hat. Unit vectors. Okay, got to take a side note on this. So a unit vector is that I hat and J hat that you saw, or in this case for the W right there. Now, a unit vector is basically just a definition of direction. So say you have your regular x and y axis units, so your unit vector is just one unit on your regular axis. It is dimensionless and it only defines direction for your scalar components. Okay, so when you had your wx and wy, those just give it direction. Okay, easy peasy. That's all. Okay, so now let's get back to adding by components. So you have ax I hat plus ay j hat, and then bx I hat plus by j hat. And when you're adding components, you're going to take those two vectors and add like components. So ax plus bx, ay plus by, and you're going to keep that same direction. This is actually really great when you need to find specific numbers for your scalar components. Okay, so let's go ahead and do a example of adding by components. So we're going to use the same vectors that we had before, but because we only had the magnitude and direction, we need to calculate their components, their scalar components. So we plug it into those same equations and just plug and chug all the way through, get our components, and then we're going to add the like components. Okie dokie. Now look at the math that's going on here and be mindful of, again, keeping your calculator in degrees and watch your significant figures. Okay, so a plus b plus c looks something like this. You start out with 0 I hat plus 3.5 centimeters, j hat, go all the way through, and you want to add up all your i's and all your j's while at the same time keeping their same directions, okay, because that's important. And so your resultant vector r is going to be 6.9 centimeters I hat plus 9.2 centimeters j hat. Yee-hoo! Okay, so the force table. This is the main tool you will be using throughout this entire lab. So you're going to go ahead and you're going to notice that there are degrees all around the circumference of the table. That's what you'll be measuring your direction. Pulleys is where you'll be hanging your masses. There should be 4. If there's 5, get rid of 1. It's really important that you know how to manipulate this force table because it's going to be so much part of your experiment. Okay, so the 0 degrees and 90 degrees can be thought of as your x and y axis. You're going to really need that in part A of your procedure. So the physics behind the lab today, actually really cool. You're going to be talking about the total forces acting on an object being 0. Okay, so you're going to have this ring in the middle of your force table, and there's going to be a metal stud. And you want it to center. You want that ring to center around that stud. And so when it's off-centered or off-balance, the total forces acting on it are not 0. But when it is centered, that means all of the forces cancel out, and it's equal to 0, okay? In this case, it will be in static equilibrium. Cool beans? Cool beans. All right, so fast summary of the procedure today. You're going to resolve a vector into its x and y components on the table. So you're going to have vector A equal and opposite vector B. You're going to resolve it into its x and ay components. Remove vector A, and vector B should stay still. Okay, now then you're going to balance forces awesomely, and then you're going to balance forces on the fly. We're going to give you forces, and you're going to be like, hey, wow, this is awesome. I'm like, yeah, I know. And then you're done. Yeah, that's it. Have a good week. Bye-bye.